Hi, this is Mrs. Daisy, and in this screencast we're going to talk about classifying chemical reactions. So if we look at chemical reactions, they basically can all fit into 5 different categories. So this particular slide only has 4 of those, but on our next slide we'll add in the 5th one. So one type is that you can have particles combine to make one new compound. Sometimes you have one compound that breaks apart and gives more than one product. Sometimes you have some combinations changing. So here we start out with orange and gray plus the green. We end up with orange and green, and then with the gray by itself. Down here, you can see that these two switch which one they're combined with to get 2 new products on the bottom. So that's one example. One way we can look at this is we can put this in terms of A's and B's. So this is kind of a standard format for these different types of reactions. So our first one we call a synthesis reaction or a combination reaction. So this is when we have more than one reactant and it gives us one product. Sometimes there's just 2 of these. It could possibly have more than 2, but your big thing to look for here is synthesis reaction only has one product. For a decomposition, it's kind of the opposite, where you have one reactant and then it breaks down into 2 or more products. So again, it's not decomposition always going to be one thing on the left, but sometimes it's 2 things here, sometimes it's more than that. For single replacement, we have an ion that's switching places. So we have a compound here with an element, and then this part of this compound joins the other element. So notice the X switches partners basically. So it starts out with the A and then ends up with the B. Double replacement, it's switching partners. So we've got AX and BY. Then on the product side, B takes the X and then A goes with Y. The last one that wasn't on the previous slide is something called combustion. Combustion is when you have a hydrocarbon, and all a hydrocarbon is some CH compound. Sometimes it'll even have oxygen in there. When that reacts with oxygen, we always get CO2 and H2O. So a combustion, the classic sign that it's a combustion reaction is your products are going to be CO2 and H2O. There's 2 different types of combustion. What we will do is we're going to assume complete combustion when we write our reactions, but just so that you're aware, there is something called incomplete combustion. The difference between these 2 is what the product is. So complete combustion produces carbon dioxide. Incomplete combustion produces carbon monoxide. So carbon monoxide, we all know, is very dangerous. That's something to produce in your car. That's produced if you have some kind of gas leak in your house, because usually what determines which of these happens is how much oxygen is available. If there's unlimited oxygen available, then usually we have carbon dioxide, but when there's not enough oxygen present, we can end up with carbon monoxide as our product. Okay, so let's look at a couple examples here to see how to do this. So if we're going to predict our products from the reactions, this is how it works. So the first thing you have to do is figure out what type of a reaction is it. So if you have elements by themselves, the only thing that these 2 elements can do is combine together. So when we come up with the products for this, we go back to our whole rule of crossing charges. So when those 2 combine and they make their formula, it's going to be the formula that, just like when we learned all of those writing formulas and naming things that we did before. So what happens over here is we look at the charges. So aluminum we know is a +3, oxygen is a -2, so we're going to crisscross those charges. So we end up with Al2O3. So when you have aluminum reacting with oxygen, we get Al2O3. And then our last step is we have to go back to what we did in the previous lesson and we have to balance it. So I'm not going to take you through the step-by-step for the balancing, but I'm going to go ahead and write the complete balanced equation. So once I balance it, I end up with 4 Als, 3 O2s, and 2 Al2O3. So again, we're not just sticking these 2 things together. When we write the product, we have to go back and think about when those 2 things combine, what is the correct ratio based on their charges. Same deal for this one. So I have sodium and chlorine. Sodium's a +1, chlorine's a -1, so we end up with NaCl. And then if I balance this, just like I did in the last lesson, I end up with 2 and 2. Okay, so those are how we predict products for our synthesis reaction. Our next thing we want to look at is decomposition. This one is a little bit trickier because this one you kind of have to memorize the formats. Now, they're kind of easy once you kind of look at those compounds and figure out what's going on, but in the beginning you kind of have to memorize what you get. So the first one, and they do follow patterns, so it's not super difficult. So when we look at this, the first one is a metal carbonate. So metal carbonate just means that you have some metal, in this case it's calcium, this could have been sodium, potassium, magnesium, any metal combined with a carbonate. So when those decompose, these are our products. We get a metal oxide, so whatever this original metal was, we get that combined with oxygen, using our plus and minus charges, so calcium and oxygen is a +2, -2, so we get CaO. And then our other product is CO2. Another type of decomposition is when we have a metal hydroxide. Same deal down here. Some metal, calcium, sodium, potassium, whatever, combined with a hydroxide. So when you see that, those decompose into a metal oxide again, still my CaO, +2, -2, and this time we get water instead of CO2. So metal carbonate, we get the oxide and CO2. The hydroxide, we get the metal and H2O. And those two happen to be balanced the way they are. Okay, my last one here is a metal chlorate. Again, any metal combined with the chlorate. Those decompose into a metal chloride. So Ca is a +2, Cl is a -1. So I get CaCl2 plus O2. And then for this one, to balance it, we need to put a little 3 in front of that O2. Okay, so again, decomposition, you have to memorize the patterns. So metal carbonate, we get an oxide and CO2. Metal hydroxide, we get calcium oxide and water. Metal chlorate, we get a chloride and oxygen. Okay, single replacement is when you have a positive or negative ion switching with another positive or negative ion. Okay, so here we're going to have an element by itself in a compound, and then that element is going to change places with the element most like it in the compound. So if the metal usually, or if the element usually has a positive charge, it's going to take the place of the positive ion in the compound. If that element usually has a negative charge, it's going to take the place of the negative ion in the compound. So to look at the example, our first example, we have copper and silver nitrate. So copper is a metal, and so is silver. So copper is going to take the place of silver, and then silver is going to be on its own. So we're going to go ahead and take silver out, so it's just silver metal by itself, and then the copper is going to combine with the nitrate, again going back to our charges to figure out what the formula is when those two things combine. So this one you would have to know whether it was copper 1 or copper 2, so let's assume that it's copper 2. So copper's a +2, nitrate's a -1, so it would be CuNO3 2. So when they switch, when they go across this arrow, you kind of think of them as breaking up in solution, and then they recombine on the other side. So to balance this one, I would need a 2 here, and I would need a 2 in front of my silver. Okay, an example of a negative ion, if I have bromine, this time it's most like the negative ion in this compound. So instead of taking the place of the first element, it's going to take the place of the second element. So in this case, iodine comes out on its own, and then sodium combines with bromine. Again, the positive ion still is first, just like always, but this time, since this is usually negative, it takes the place of the second one. So I end up with Na +1, Br -1. And then to balance this, I need a 2 in front of there, and I need a 2 in front of my NaBr. Okay, next example is double replacement. This is when the ions switch places. So they reform on the other side, still positive ion with negative ion, but basically you can think of this as kind of switching their partners. So I have sodium chloride here, silver nitrate here. So the sodium is going to take the place of silver. So the sodium is going to combine with the nitrate, and then the silver is going to come over here and combine with the chlorine. Again, when we're predicting our products, we still take into account what the charges are when we're writing out the formula. So in this case, I would get silver nitrate, NaNO3, which is a +1 -1, and silver chloride, which is again +1 -1. So this one ends up being balanced the way it is. My other example for double replacement, I have Ki, potassium iodide, and lead nitrate. So potassium is going to take the place of the lead, and then the lead is going to take the place and combine with the iodine. So I end up with potassium nitrate, and lead iodide. Okay, and this is lead 2 iodide, which we could have figured out from here, or the problem could have told you that. And then to balance this, I need a 2 over here, and then I need a 2 here. Okay, my last type is combustion reactions. These are the easiest type to write out. These are the ones that are a little bit more challenging to balance. So if you have a combustion, no matter what we say the reactants are, if it's a hydrocarbon, so carbon and hydrogen reacting with oxygen, the products are always CO2 and H2O. So if we look at this, the first one, CH4, which is our hydrocarbon, it's this methane, natural gas, reacting with oxygen, we get CO2 plus H2O. My next one, C6H14 plus O2, hydrocarbon plus oxygen, products, CO2 plus H2O. Last one, C2H5OH, okay, still a hydrocarbon, this time it's an alcohol, it's got this OH group which makes it an alcohol, but the CH still makes it a hydrocarbon, plus oxygen, CO2 plus H2O. Okay, and then I would go back and balance these. So my first one, I would need a 2 here and a 2 by the water. Next one, this would be a little bit, like I said, more challenging to balance. You end up with 2 of your hydrocarbon, 19 oxygen, 12 CO2, and 14 water. And like I said, these are the ones that we said can have much larger coefficients. And then the last one, I need a 3 in front of my oxygen, 2 CO2, 3 H2O to balance.